Let me tell you what I'm doing today, guys. I'm checking the project DR100 concept project. The test is specific to the digital volume control runs by the TDA7449L, and these boards in here. This is the equalizer module, digital volume control IC, which is the TDA7449L. There is no equalizer in here. And this is the control module, which is controlling the equalizer module. The test interface right now, I'm using the multi-instrument from Virtins Technology. Those guys from Singapore develop this hardware in here, the hardware interface, which is a PC base. And this multi-instrument hardware is the DSO QA401. The USB interface is connected to one of the USB port on the PC, and we got here right now the output signal, which is connected to one of the input of the project. And the channel 2, or yes, the channel B, I'm monitoring the input using this oscilloscope probe in here, which is the green one on the application software on the PC. And then the output is monitored in here, the output of the digital volume control, and it's monitored on channel A. So that is the yellow one on the multi-instrument application software. So that's basically the setup right now. It's really easy, convenient, and compact. And the setup is not complete without the 220 volts household AC power. And currently right now the setup is consuming about 2.8 watt from the AC household line. That is a 220 volt multiplied by 0.024, and the power factor is a 0.5, and it yields you to 2.8 watt of power. And there you go, is the switch mode power supply, which is 15 volts output, which power the control module over there, and the other one is the equalizer module. Again, you can see the PCB don't have that IC, which actually that one is the equalizer IC, which is the PT2389. Alright, the iWires, let me dive into the test on the PC screen. And we got here 3 windows. The first one in here is the oscilloscope, and the one in the bottom is the spectrum analyzer window, and the one at the right side is the signal generator, and it is set at 1 kilohertz, and the output is set to about 1.5 volt RMS. And I trained that one to get an output of about 1 volt RMS. That's what you can see in here. Let me increase that one on the oscilloscope. So on this side, you can see 1 volt RMS output, which is this one. You can see the signal is just like jumping. Well, that is normal because it looks like that the inside the generator, the audio frequency generator, it looks like resetting or something like that, like it's breathing. That is the right word. And I can minimize that one, the oscilloscope, so I can see the spectrum analyzer. By the way, the yellow one signal right now you are seeing here is the output. All right, let's go back to the spectrum analyzer, and we can see in here this is the 1 kilohertz signal, which is 2, what is that? It's a 2 kilohertz, and the other one in here, it's a 3 kilohertz, and until to 500 kilohertz. So that's how it looks like. And the other parameters that we can see in here is, you can see this one in here is the distortion, which is the output distortion is a 0.3%. Well, let's just take note of that. That's not bad distortion actually. It's a 0.3%. But comparing that with the Megoro distortion meter, I found it out that the distortion of this multi-instrument with the DSO QA401 is higher than the QA401. probably because of the resolution, which is just only here is about 16-bit. So I just take note of this information, and we can see the input as well, which is connected to channel B. Let's expand that one into, okay, maximum maximum window, I should say. And there you go. So we got an input of about 1.05 volt RMS, and we got an output also of 1.0 something RMS. So basically the input is equal to the output. Of course, this is the sine wave, and I can switch to square wave, but the FFT, I don't need it, so I can either close that one or just minimize it, and then emphasize the oscilloscope. And then on the signal generator, I'm going to change that one into a rectangle, and that's how it looks like at 1 kilohertz. I can actually expand this one to 5 milliseconds, and that's how it looks like. And of course, I can change the frequency to 10 kilohertz, which is already preset in here. And that's how it looks like for the 10 kilohertz. And let me put the one into 100 microsecond, 200. I can see already that the output lags the input with the sum, probably that is in nanosecond. How to measure that one in here actually? That is a question. I'm still studying actually, so pardon me for that. Let's put that one to 400 microsecond for the sweep. And we got here the comparison of the input, which is the green one, and the output is the yellow one. So if I'm going to put that one in the overlay with the same voltage magnitude, we can see in here it's quite nice actually. Now it's time for me to put the frequency counter, which is at 10 kilohertz. As you can see in here, I can notice already that the output really logs the input for some again, maybe microsecond or nanosecond. This is at 20 kilohertz and goes up to like 50 kilohertz. And there you go. So the higher the frequency, the higher the time that's the output lags the input. 100 kilohertz and still goes up to 200 kilohertz. There you go. It's still square wave. Let me put that one into something like 20 microsecond. Oh, that's terrible already. You can see already in here the rise time and the fall time. That's really quite bad already. But of course, 200 kilohertz is way above the 20 kilohertz, the limit of the audio spectrum. What probably more interesting to see is on the lower side, like let's say to 500 hertz. So 500 hertz, 100 hertz. Yes, it is more evident on 100 hertz, where you can see the yellow one is we've got a loss of frequency. So this side is the high frequency and this side is the low frequency. So as you can see, the input is still almost like a perfect square wave, but the low frequency component of the output right now, it goes down, as you can see in here. This is the signal at 50 hertz, and you can see the lower the frequency now is that there is a frequency loss, as you can see in here. So I'm going to put that one into 20 hertz. And there you go. So it's evident right now that there's a loss of frequency at 20 hertz as compared to the input signal. You can see this one in here. I really hope that the signal waveform generator will not like breathing like what we have right now. Maybe I'd like to use the AF generator in there. This one here. This is the audio generator from GW Instinct, so we can actually see without the breathing effect. Yeah, this is the one. Actually, this is the output of the multi-instrument, and I'm going to remove this one. So the signal output It's no longer an input, and I'm going to put the one in there, which is I'm going to put that into square wave. First is to put it at 20 hertz. That is 20 hertz right now. There you go, sir. And put that into square wave, and we can have it right now, the non-breathing effect. If that is the right word. So we can see in here is a stable. Let me position the camera into a better angle, so we can see in here. Maybe there is also, no, I was thinking about there is a cursor in here. You know, guys, I actually don't read the manual yet. I haven't scanned it. I just tried to use it, and really crazy to use it as soon as I get it. And without using the user manual, then I can easily navigate it, which one is which. And there you go, and there you are. There is one more thing that we can actually measure in here, which is the noise level when there is no input signal. That means, let's just say 0 input signal. So I can set the amplitude of the AF generator to 0. And what we can get in here, this is the noise level. Basically, I don't need the input this time, so I just only need to monitor the output. 16-bit. There you go. So the yellow one is the output. So this is the signal level. Let me emphasize that one. Oh, there is my reflection in there. Hey guys, hello everyone, wherever you are. Good morning, good evening, have a nice day. There you go. You can see my hands, right? And my clothes at the top. Let me put that into a better captured by the camera without showing it my back and my face and my clothes at the top. And this is the noise level right now of the amplifier. Not the amplifier, the equalizer module running the digital volume control. And we can see in here that's very like minus 105. That is a dBF. The only remaining question for me, which I need to clear it up, is about the distortion, which is over there. And I don't believe that distortion actually, which is the input, is about 0.7%. So the thing I can do right now is to clear it up, making use of the Megoro distortion meter, which is always been my partner in terms of distortion, which I believe it. So what I'm going to do is to remove this output from the DSO 20E, and I'm going to hook that up to the Megoro distortion meter. And what we can have it in here. And there you go. Well, I told you guys the distortion, I mean the multi-instrument DSO 2-way 20E is sometimes like breathing, as you can see on the distortion in here. And let me see the setting. It's a 3%. First is the voltage swing. This is set at 3, and that is 3, and there is about almost like 1.1. What do you read, guys? I read it about let's just say 1 volt RMS. And for the distortion, we got 0.3 right now. Okay, 0.15, 0.16. So let's put it into 0.1. And what we can see in here is we got a maximum of about 0.07. As you can see right now, the input distortion is about 0.7, the green one, and the output is about 0.3. Oh, why don't we see the output as well? That's a good idea actually. So the output is this one in here. Let me put the tripod. Okay, there you go. The tripod is in there. All right. So I'm going to get the output right now and then put it into the distortion meter. Okay, set it first to maximum distortion reading, and there it goes. Okay, the breathing effect is, I'm reading here at maximum about 0.09. It peaks at 0.09. Let me show to you what I mean by that and focus it. There it goes. The maximum, this is a 0.1, that is a 0.09, so it goes into 0.09%. Alright DIYers, this is my demonstration of the performance, a short electrical performance of the digital volume control using the TDA7449L of the project, the R100 concept project, and I hope you learn from it. And if you like this kind of video, you might consider to subscribe. That will help me a lot here at YouTube. And when you subscribe, you click the notification bell so that when I have a new video, it will alert you that I just posted a new videos. All right, thank you for watching, and thank you for your support. Bye for now, and see you in the next video.